All right, ladies and gentlemen, welcome back to our newest video, our second video in this unit on electrostatics, sort of charge, force, and field for electricity. This video is dedicated to the ideas of conduction and induction. These are both ways in which we can transfer charge or change the charge on objects besides just rubbing and physically stripping away those electrons like we talked about in the last video. Just to review which part of the atom is transferred during the charging of an object, that's the electron. We're only moving electrons here. And one of the best things we can do is just think in this situation, especially for this this video or this sort of lesson, what are the electrons doing, right? We don't care what the protons are doing. What are the electrons doing, and what does that mean for our object? Second, two objects of differing charge are brought in contact after. The total charge has to be equal to before. We have the conservation of charge. Conservation of charge. Charge is conserved. It stays the same overall. Individual objects can gain and lose charge, but your system of objects, all the objects you're talking about, cannot lose any charge. And last one, sphere A is carrying a charge of plus 4 coulombs, and an identical sphere of B is carrying, it looks like negative 2 coulombs here. So if we got these two objects, if they touch each other and then they are separated, what's the charge on sphere B? First, I would take a look and say, all right, what's my overall, what's my net charge? So I do 4 plus negative 2, and I get an overall charge of 2 coulombs. And then if I touch two identical spheres together, they split that overall charge equally. So in order to split that charge, in order to get it to add up to be 2 coulombs, I've got to have 1 coulomb on each object, 1 positive coulomb, 1 coulomb of positive charge there to match up. So after those two objects touch, the charge on sphere B is plus 1, and the charge on sphere A is plus 1 as well. So the first thing we want to hit today is the idea of conduction. This is charging by touching two objects, one that's neutral and one that is charged. And in order to do this, we need what's called a conductor. This is a material that allows electrons to flow easily through it onto other conductors. Metals are perfect examples of conductors, things that conduct electricity. That's why the wires in your wall are all made out of metals. Typically copper a lot of the time is used for, copper wire is used often because they allow electrons to flow very easily. And we can charge an object by passing electrons through conductors. If we connect objects together with a conductor, we can pass electrons through them, and that is called charging by conduction. And that last problem on the last slide, when we touch those two spheres, they are charging by conduction. And we say that an object is grounded if we actually connect it to the earth with a conductor. If I connect something sort of out of my system into, to the earth, that lets me lose electrons from it to the earth. If I ground an object, I'm resetting it to neutral. If I ground an object, it becomes neutral. That's because electrons want to be neutral. Like, that's their normal state. They're happy being neutral. They're happy matching up with those protons and having the equal numbers. So if there's any way for them to get away, they take it. And if they can get back to the earth where the electrons are so spread out, that's where they want to be. So if we ground an object, we connect it to the earth with some sort of conductor, it becomes neutral. And that's going to be important for the ideas of induction. Important for induction, which we'll get to here in a minute. So with induction, I've got this little interactive here. Let's see if we can pull it up. And we saw this in class as well. We've got this aluminum can, and we don't actually know what the charge on it is. But I do have this glass rod, and it says that's positive charge. So I bring it kind of around and realize that this positive charge is attracting my can. And I said that positive charges attract negative charges, opposite charges attract. So my first guess would be that this can has a negative overall charge on it. And it's like, well, that's pretty great demonstration. There's not much there. So if I put this rubber rod, and the rubber rod is going to be negative, I should see that this can is repelled, but it's not. If I bring this negative here, the can is still attracted to it, which leaves me really two explanations. Either the simulation is just wrong, or there's something else going on here. So I'm going to actually show the charges on this can. And as I bring the glass rod, the positive one, all the electrons, those free-flowing electrons that we talked about in the last video, keep shifting to be towards that positive charge. They want to be there. So what I end up with is this region here on the left of the can that is very negative. But then that leaves on the other side a region where the protons are still locked in, they can't move, a very positive charge. We call this idea charge separation. We separate charges by bringing a different charge involved. And it works with the rubber rod as well. If I remove this glass rod, I can see that these negative electrons, this negative charge on the rod, pushes away all of the electrons. They don't want to be next to it, and it leaves still this very negative region on the left and a positive region on the right. So let me go and back out of this, and we can take a little explanation of what is happening here. We're going to skip over induction because first I want to talk about what is called charge separation. And charge separation is what we just saw, and the best way to do sort of diagram this is with an electroscope diagram. And these are those little boxes that we have in class with the little bulb on top and the leaves inside the box. If you have any questions about it, please just come see me. I can show you what I'm talking about. But we diagram these with these little stick figures without any arms. And we saw that if we brought charged objects close to but not touching the bulb, that sort of circular part at the top, that the leaves would separate. And that's the exact same thing that we saw in that Coke can video. So let's say that we start off with a very neutral electroscope. It's got positives and negatives that are all balancing each other everywhere. Positive, negative, positive, negative, positive, negative. It's all good and dandy. But let's say then now that I brought in a very positively charged object very close to it. Brought it real nice and close. If I bring that charged object, the electrons are going to get attracted to it. So all these electrons that were down here, and I can't really pull them, so I'll erase them. All the electrons that were down here are going to rush up to that top bulb. Now they can't actually get anywhere else besides that bulb, but I get all these electrons, these negative charges that get pulled up, and I get this very overall negative region up top. Down below, we're left with no electrons, so I get two positive leaves, so it's proportionally more positive. There's no extra protons that got there, but there's no electrons to counteract those. So now I've got two leaves with the exact same charge on them, and they separate. Because those charges are alike, they separate. The same is true if I had brought a negative object in. Let's say instead this was a negative object. Well, instead of being attracted to this negative object, the electrons, I'll just redraw this whole thing because it's all messed up now. But if I started off with a neutral electroscope beforehand, if I bring a very negative object in, there we go, very negative, those electrons, I'll bring it a little closer here. Get him in right there. All those electrons aren't going to want to be on that bulb, so they're all going to move down into these leaves as far away from this very negative charge as they can. So what I end up with is neither of these guys, if I can pull them out a little bit or erase them, they've moved down. So I get this very positive region up top and a very negative region down bottom. And when we're drawing those diagrams, we just would leave off these two positives. We would just say, you know what, there's enough electrons down here that those two positives, we're not even going to draw them. We would just say it's very negative over here and very positive here. There are still some protons down here, but there are so few of them compared to the electrons, we're not even going to draw them. And when we get these charges separated, we can actually do something to make this sort of permanent. Because if I take this ball away from here, this negatively charged object, if I take it away, Well, now those electrons, they're not really happy being all down here by themselves, all the electrons together. They're going to rush back up, right? They're going to re-neutralize this electroscope. But if I want to permanently charge it so that those leaves are spread apart, I have two options. Either I can take that bulb, and now I've got it all messed up, but if I take that bulb and I actually touch it to that sphere on top, if I touch it to that sphere on top, I'm going to get electrons that actually rush off of the sphere and onto this bulb to try to neutralize, to try to cancel out all those positives. And then when I take it away, I've got more electrons now than protons, and I've got this permanent negative charge. That's charging by conduction. So when I charge by conduction, when I actually touch something, whatever charge my object was, object charge, my electroscope is going to get the same charge. So these two charges are the same if by conduction. But when we get this charge separation, we can actually charge by what's called induction. We can get this induced charge. We induced that charge separation, and now we're actually going to change the overall charge of that electroscope. So I'm going to zoom over here a little bit. And we have a couple of steps to induce a charge. I'd recommend getting these memorized. So the first goal is to ground the object. You want a very neutral object to start with. You don't want one that has a charge already on it. You want it completely grounded. But then next up, you have to unground it. If you don't unground it, then it will just stay neutral. We said that when we ground objects, they become neutral. So if it continuously stays grounded, that's no good. It'll just stay neutral. We don't want that. So then we're going to bring a charged object very close to, but not touching, just like we did when we got that charge separation. So if I'm going to draw that out, let's say I had a neutral electroscope, but I'll bring in a very positively charged object. So on the electroscope now, I've got a very negative region up top, and down below is very positive. So that's what happens after number 3. So for number 4, I need to touch the side of the original object that is not near the charged object. So I'm going to touch this side down here. The bulb up top is where my charged object is, so I'm going to touch the leaves. And when I do that, I'm actually grounding those leaves. I'm grounding that side of the object. Well, I've got a lot of positive charge down there. And if I ground it, electrons from the ground are going to rush in to balance out that positive charge. The electrons are already sort of locked up top, so extra electrons will actually pour on to neutralize this. And I get more electrons than I started with. I actually end up now with more electrons than I had to begin with. So when I remove this charged object, there we go. When I remove this charged object up top, now overall I've got more electrons than protons. I have a now permanently negatively charged object. So you end up with an opposite charge when you induce an electric charge. So you end up with opposite charge. If you are charging by induction with a positive object, you end up with a negatively charged object. And if you start with a negative, you end up positive. You get the opposite when that occurs. Here's a little diagram to see it a little bit better. First, a metal sphere, just completely neutral. We bring in this negatively charged balloon here, and we get this separation of charge. We get very positive on the left, very negative on the right. It's positive on the left because those positives are still there, but the electrons, those negatives, were repelled by this negative object. We touch the side that is not close to our charged object. So those electrons leave, in this case, it's the opposite of what we talked about on the last example. The electrons actually leave. They're too crowded up. They want to get out. So now we have a overall positive charged sphere, right? We got rid of some electrons. We just can't necessarily see it yet because we've got this negative charge here as well. But when we take that away, we end up with a very positively charged object that sort of spreads everything back out and redistributes its charge. And I believe that takes care of the ideas of conduction and induction. This part of the unit, these first two videos, have been very conceptual in nature, and the first part of the test that you're getting ready for is also conceptual. 15 questions are just like these. Can you recognize which diagram represents this situation? What type of particle gets moved when we talk about an object being charged? Those types of questions. In the next couple of videos, we're going to be talking about the actual math behind this instead. If we're going to have objects that move like we have these repellings, we've got to have a force to go with it. Objects don't just move on their own, so in the next video we'll talk a little bit about electric force, and we will see you then.